Now we can move on to gradient boosting. So gradient boosting was originally proposed by Jerome H. Friedman in 1999. And there's two papers you can find online. One is called Greedy Function Approximation and Gradient Boosting Machine. And I think that was like more of a lecture that he gave because it was like 40 pages or something like that. And the second paper you can find is Stochastic Gradient Boosting. So those are this is the person that created it. So what is gradient boosting and how is it different to bagging, bootstrap aggregating, and AdaBoost? So the main thing with gradient boosting is that this time we're not just going to adapt, we're going to actually changing our sample. We're not going to be doing any bootstrapping. So we're working with the original sample all the time. That's very important to understand. There's no bootstrapping and gradient boosting. So what you do in gradient boosting is we're going to look at gradient boosting for regression first. So you have your 1,000 customers that you can. I can't believe this example stuck. That was just a random thing I wanted to do for the trees. So you have these customers, 1,000 customers that bought candles from your store. You want to predict the future customers and so on. So what you do for the first, the future spend of customers. So your target variable is your dollars spent. So what you do is you take as your first step. So again, it's gradient boosting is again going to be an ensemble of models. Your very first model is just an average. It's a simple average. You take the average of all of the dollars that all of your customers spend, and let's say you get something like $57.50. Oh, let's say just $57 for simplicity's sake. That's the average of all your customers spend. So next, what you do is you calculate the errors, right? So you look at, okay, $57 is my average. That is, of course, a terrible prediction, terrible kind of model. You just took an average. So for some observations, you'll have an error. Some observations will be lower. Some observations will be higher. So you basically calculate the error for each one of your 1,000 samples. And then you take those errors, right? Whether it's the error was $2 or $20 or minus $100, you take all of those errors and you build a decision tree to predict those errors, right? So with the first model takes the average, works with the sample. The second model, which is our first decision tree, it will work with all of the errors that you got as a result of the first model. And now this decision tree will be structured in some sort of way. It'll make its own predictions. And now you will have, again, errors. You will have errors of this decision tree's prediction. And some might have $5 error, some might have a minus $50, minus $100. Again, you look at all the errors of the predictions of this second model, which is a decision tree. And you use those errors, and again, you'll have 1,000 errors. In some cases, it might be zero, but you'll have 1,000 values, and you use those errors, and you make another decision tree. So your third model will also be a decision tree, and it will predict the errors of the second model. And then you build a fourth decision tree, which will be predicting the errors of the third model. Then you build a fifth model, which is also a decision tree, and you predict the errors of the previous model, and so on. So you chain them together. Like the key word here is you chaining models after each other. The first one is an average, and then it's decision tree, like up to 100 times, however many decision trees you want. And each one is just focusing on predicting the errors. So what's the point of that? Well, guess what? Well, now, if we, as our final model, we're not going to take the average, we're not going to take the weighted average. As a final model, we'll take the sum. So you'll take your first model, which is the average. You'll add the result of the second model, which is whatever the decision tree predicts for this kind of variable, right? So let's say you have a new customer come into your store, and you want to predict how much they will spend. The answer will be the average, which was, $57, plus whatever the next model number 2, which is a decision tree, whatever it predicts, plus whatever the next decision tree predicts, plus whatever the next decision tree predicts, and so on. And so you add all of that up, and because each time you're predicting the errors, so now like your prediction is like the average plus what would the error be for this person that just came in. Okay, the error for this person is 57. Okay, based on their age, based on the income, whatever the decision tree is looking at, the error of this initial model would have been minus $101. So you need to add that, right? So you go from 57 minus 101. I'm not that great now. 40, what is it? Minus 44, right? Is that minus 44? Yeah, minus 44. Then the next model will be, okay, what would have the error been based on of that prediction? The previous one, the error would have been like $50. So now you go up to $3. And then the next model says the error at this point is about $27. Now you go up to from $3 to $30. And so on, so on, so on. And then the final result is like, okay, so this customer will most likely, based on their features, based on what the model predicts for them, this customer will likely spend $39 in our store. So that's how gradient boosting works. You're basically chaining models to constantly just predict the errors of the previous one. And that means in the resulting model, you need to just add them up. And each prediction will be prediction of the errors. And in the end, you will get your final result.
Nice. Very well explained.
It's probably, I just had this idea. It's probably good to call the first model, like the average, call it model 0. And then you can, like, because otherwise it's confusing. Like the first decision tree is the second model, the second decision tree is the third model. So it's like model 0 is your average, and then model 1 is a decision tree, model 2 is your second decision tree, and so on, so on, so on. And the final result is the sum of this chain. So as you can see, it's very different to what we had previously in the bootstrap aggregating methods, which were the bagging, basically the random forest, the way we took the average. And it's also different to the boosting method of AdaBoost, where we took a weighted average of the models. So AdaBoost is kind of in between. It's like it's used as bootstrap and it's used aggregating. So it's a bootstrap aggregating method from the sense of how the samples are built, but it's a boosting method based on the concept. So AdaBoost is like a transitional, whereas gradient boosting is pure gradient boosting. There's no more bootstrapping, straight into, okay, use the same data set all the time, and but you focus on improving.
So I guess kind of to summarize back, so the random forest is random. You're not trying to do like this went into your kind of democracy versus
Yeah,
meritocracy
yeah,
example. With a random forest, you are randomly creating a whole bunch of decision trees, and the more that you create, you get this slight marginal improvement. Like when you go from 1,000 decision trees, random decision trees, to 1,001, there's this very marginal improvement. The core idea with adaptive boosting was to not be randomly creating these decision trees, but to use some information like which data points were misclassified previously, and let's overweight those in the previous model. Let's overweight those in the subsequent model, so that we're consciously iterating in the right direction, adaptively, boosting. Then gradient boosting takes us another level further by not just saying, let's focus on the data points that were misclassified. Let's look at the residuals, like the specific delta between what the correct answer would have been and what the model predicted, and let's fix those residuals. So you're focusing on where the most possible opportunity for improvement is, and that's why gradient boosting is so powerful.